Hi everyone, thank you for joining us today. My name's Nick Bray. I'm with NBA, an architectural studio based in both Vancouver and Victoria. I'm speaking to you today from Vancouver, which lies on the unceded traditional territories of the Musqueam, Squamish, and Tsleil-Waututh nations. At NBA, our mission is to contribute positively to both society and the environment by designing innovative, sustainable, and community-centered buildings. The purpose of this seminar series is to offer an overview of timely and relevant topics impacting our work and hopefully yours too. We've aimed to make the presentations more practical, focusing on how we can apply the lessons directly to our day-to-day work. So after this seminar today, which is the last in this kind of three seminar series. We'll be taking a break for the summer, but we'll return in September. We've already started planning and lining up some lectures, the first of which will be likely be on how to implement artificial intelligence into our workflow. We've just started planning a lecture about applying Indigenous cultural awareness into everyday architectural practice. We may look at have a seminar looking at some of the new zoning bylaws in BC, including the transit orientated communities. And then also we'll hope to keep giving you working with Celerity Engineering, giving you updates on any building code related subjects. If you have any suggestions for future seminar topics related to challenges that you're facing in your work, then please feel free to share them in the chat box or send us an email. You can also use the chat box today, please, to ask any questions. There's a lot of people on this attending this seminar, so we can't unfortunately can't have everyone speaking. But if you put the questions in the chat box, then we'll get them to them either throughout the lecture or at the end. So we will be, I think we'll be putting the link to the AIBC accreditation form. If you're looking for your AIBC CPT points, that will be put in the chat box probably about halfway through the lecture and then again at the end. It's a simple form, so just have your AIBC number ready. Thank you very much for filling out the polls. Just look at the results here. We've still got 80% architects, but we've got a lot more structural engineers. So welcome to the structural engineers here today. So let's get started. I'd like to introduce Leon Plett. Leon is a highly respected structural engineer and managing principal at RJC's Victoria office, known for his creative, economical design solutions and strong client relationships. He specializes in seismic upgrades of heritage buildings and timber construction, with notable projects including the Hudson Bay redevelopment and the Brentwood College Visual Arts Centre. A passionate volunteer and active industry member, Leon has contributed his expertise both locally and internationally on a range of impactful projects. So thank you very much, Leon, for joining us today, and yeah, take it away.
Thanks, Nick. Thanks for the opportunity. I'm really excited about this and maybe a little nervous. 300 architects or 169, that's a lot. I probably know many of you. Please bear with me. I'm not, I'm a great engineer. I'm not necessarily the best presenter. So I'm gonna do my best here to walk through some of the seismic changes in the most recent code update. I know this has been ongoing discussion as the code has been on again, off again for a while. So we're going to chat through what those changes really mean in our building design and some of the ways we can adapt to those changes. I'll give some background and some learning on where those changes came from as well. And then hopefully we can talk through some practical solutions and some options as we get further along in the presentation. If I could advance the slides, that'd be great. Here we go. Okay, as Nick said, here's some of the housekeeping information, the updates. I had a chance to look through some of the other presentations. They were great. Would recommend going back and taking a look at those presentations that Nick's team has put together. Really informative stuff there. A little bit about RJC. Many of you probably know us. We started in Vancouver 77 years ago. We're employee-owned, 650-ish folks across the country. We now have one small office in the United States as well, but mostly focused in Canada and mostly focused on structural and then building enclosure and restoration design. We're actually we're sort of known as a structural firm, but we just tipped the scales on that, and we're now more of a building science and restoration firm than we are a structural firm. We have more folks doing building science work and restoration work across the country than we have doing structural engineering. So a bit of an interesting change at RJC in the last few years. Services we provide, take a look there or check our website or talk to me or anyone else at RJC. There's a lot of work we do with regard to buildings. Both from the enclosure and the structural standpoint. So we're going to jump into it, outline and objectives for today. We're going to learn a little bit about the BCBC seismic code changes. Maybe more than a little bit. We'll try to learn a lot about that. We'll really dig in on site class and seismicity and its impact on building design. We'll chat about impacts on layout, systems, and cost, and then we'll talk about some strategies and resources and some information towards the end. There's going to be, we could talk about anything. We could talk about, mass timber fire halls we're designing or state-of-the-art office buildings or all those other things. But to narrow the focus for today, we're going to focus on Vancouver Island mid-rise. This is the majority of the housing stock that we're in design and construction on right now in BC. It is, the least carbon-intensive form of construction. It's relatively affordable. Supported by BC Housing. I know a lot of us are working on these types of buildings, both on the island and on the mainland. So just wanted to narrow the focus of today's talk and chat more about Vancouver Island mid-rise. Anything we talk about here to some degree or another is going to apply to mid-rise or other building types across the province. We're going to learn a little bit about the seismicity and how that affects some projects on Vancouver Island, perhaps a bit more than other areas in the province. Okay, so the code changes. First, I want to start with letting everybody know that earthquakes are in fact real. They happen. We live near a very active seismic fault, several faults in fact. I saw from the poll that we had 0 developers on the call. It's the developer folks who tend not to believe me on this, right? They think that architects and engineers are just making this stuff up. We make up rain and cold weather and earthquakes just to keep ourselves busy. That's not in fact the case. They're real, they're risky. Our job as engineers and architects as well is to keep people safe and happy. And that's what we want to do. The image on the left is what we think of when we think of how we design for earthquakes, right? We're designing buildings primarily to avoid collapse in a major seismic event. But the thing that we often neglect to remember is that much more frequent and more significant in terms of monetary damage and business interruption is the smaller but more frequent earthquakes that cause damage to operational and functional components, other aspects of the building, not necessarily collapse or damage to life, but have real impact on people's lives nonetheless. We're going to talk about how the code is going to address this a little bit more under these new code changes. Okay, so why did these changes happen? On Vancouver Island, the main thing that changed is the relatively recent discovery of a large new fault that goes from Leech River to Devil's Mountain. This goes right through southwestern Vancouver Island, right adjacent to one of our fastest growing municipalities in Langford and through southern Victoria, and then off into the Strait. We knew this was bad news when we heard it was called the Leech River Devil's Mountain Fault, right? It's a bad scene. We know this is going to be a bad fault. And there's quite a high probability that it's active. And the way the building code adapts to the risk of earthquakes, it's probabilistic. So it takes all of the potential earthquakes and their relative probabilities and rolls that into a seismic hazard that we designed for. So the discovery of this new fault bumps up our ground motion design that we need to account for in the building code. The other thing, and as we talked about, is that lower bound value. Is measuring VS30 rather than site class. We're gonna learn quite a bit more about site class versus VS30. I know there's lots of questions and comments on that. And we're going to talk about where that VS30 is measured from. So the code changes increase the importance of geotechnical conditions and soil properties. So rather than the old step function of site class, we're moving to that VS30 calculation, which most of you are familiar with. And there's some field testing and some cost, some front-loaded cost on projects required because of that VS30 testing. Another thing the code is doing is verifying building performance under low-intensity earthquakes. So not just that collapse prevention, low probability, high impact earthquake event, but those higher probability, lower impact events that are more frequent is now mandatory that we design for those in the code for smaller buildings. It used to be only for high importance or other buildings that was included. There's some changes for buildings with gravity-induced lateral demand. So the picture on the right-hand side, those sloped columns produce a lateral load under gravity loads. So it doesn't require any wind or earthquake to induce a horizontal force on that building, and the code has gotten clear about what we need to do in those instances. There's also some code clarification around irregular buildings with sloped columns. So there's two clauses here around irregularities. One is gravity-induced lateral demand, and one is sloped columns. They're somewhat related, but a little bit different. We'll talk about that in a little bit more detail. Okay, the magnitude of the change. The graph on the left, I think, is important for people to take a look at, especially those who might practice occasionally on Vancouver Island, but primarily on the mainland, is that we saw sort of the code forces running in lockstep from the 1950s to 2020 with some changes to Montreal and Vancouver Island in 1985. But then this most recent code change really jumped up those Victoria loads relative to Vancouver. So we're almost double what the Vancouver loads are here on Vancouver Island, which is often a surprise to developers and architects who are used to practicing in Vancouver, come to Victoria and here there's twice as much shear wall. The reason is that new fault discovery and our proximity to the Cascadia subduction zone. So that's why our loads are so much higher here. I wanted to include the larger graph as well on the right-hand side, which just shows seismicity across the province. And so we know, the majority of people in BC live in southwestern BC. There is seismic risk across the province, but it does die off pretty quickly as we get towards the Rockies. I like to joke about with my colleagues in Alberta and Saskatchewan and Ontario about the ease of their work. It's not so easy. I see the towers they're designing in Ontario, and it's difficult. It's just they don't need to deal with earthquakes. Okay, so we're going to talk about site class and the seismic impact on building loads. I'm sure everyone on the call is familiar with site class, but I thought I would take a step back and explain how do structural engineers design the seismic load on a building, right? We're not just given, the code doesn't just give us, here's the seismic load that applies to all buildings. There's a formula, and I want to walk through some of these variables, and then we'll step into them in a little bit more detail. So V is the horizontal shear force. That's the load on the building. Imagine a horizontal pushing force on the building, and that's how we design for earthquakes. It's an equivalent static procedure. So we're not dynamically moving a building in our model. For more simple buildings, it's equivalent static, and that's based on the design spectral acceleration that S of T that comes from site class, etc., and the seismic risk. And then there's higher mode effects. We won't talk about that today. That's for taller buildings. There's earthquake importance factor. I think you all know about high importance and post-disaster buildings. When we're designing schools and fire halls, we use those IE values that are higher. There's W, which is the weight of the building, and you can see there's a linear relationship between the weight of the building and the seismic force. We'll talk about that at length. And then the denominator in the equation is RD, R naught. R naught is the overstrength factor. It's relatively straightforward. Some materials have more inherent overstrength than others, and that's the RO factor. The RD factor is ductility. And so that's a very, very important variable. And it's something that we work really hard to follow the code as best as possible to allow us to use the largest ductilities we can to reduce the seismic loads. And I'll explain a few of our options as we go along in the slides here. If you do have any questions as I'm going through here, I know I'm going through some complicated things quickly and some things maybe I'm dwelling on fairly long. If you have questions or comments, feel free to drop them in the chat, and I'll keep an eye on that. I know Nick's keeping an eye on those questions as well. If he sees something that maybe we should expand on, I'm happy to do that. So I thought I'd explain a little bit about shear wave velocity. When we talk about VS and we say VS30, VS is the shear wave velocity, and VS30 is the shear wave velocity in the top 30 meters of the soil on the site. That's the velocity at which the shear waves that are generated by an earthquake travel through the ground towards and impacting a building. So the higher the velocity, the lower the higher the frequency. Harder rock or harder materials have a higher frequency than softer materials, and that has a very, very big impact on how the building feels that load that sits on the soil. and it's mainly affected by soil density and relative strength. So there's a combination between strength and density. On Vancouver Island, we have a very wide variety of soils. So we have marine clay deposits in most of Greater Victoria, overlying bedrock. So we have sites with very, very soft marine clays, like where the Empress Hotel sits on very, very soft marine clays. That's why we have such big subsidence on the southern side of the building. But 2 blocks away, we might have a building founded on hard granite. So there's a very big difference, and we'll see how much that affects building design. Again, VS30 is the average in the upper 30 meters underlying a site. And it's the parameter used to define the reference ground condition site class, again from A to F. Used to be assigned as a site class. Now we can use the curvature value from VS30. I thought I would also include on the right-hand side here, this is a map of Greater Victoria and one aspect of seismic risk, which is slope stability and liquefaction potential. These maps are all available from the BCGS. Maybe we'll include a link at some point here to all of these maps. There's seismicity maps, etc. I wanted to include it just to show the high variability. It's the reason I tell, every client, architect, developer that they need to talk to a geotechnical engineer as soon as possible. Being even half a block away from another site in Victoria could completely change the building design parameters. And I see a question here from Rob about site class. Well, we're going to talk about that a little bit more here as we go through this. So here's my nice little graph about site class and VS30 about this is how it's changed. So site class used to be a step function. So we had site classes A through E, A being hard rock, E being soft soil, and F being other soils, which required site-specific analysis. It was a sort of a different category. And so we had this step function. What happened was the geotechnical engineer in their reporting would do their site investigation and give us a value for site class based on the type of soil on the site. And so those are the site classes A, B, C, D, E, and F. And that's the way the code treated the soil structure interaction until the last iteration. And what we have now is we have VS30. So the pink line is the VS30 curve, and you can see it correlates relatively well with site class, but it has a specific value at every particular frequency. We don't have to use that step function. So you could see where we used to be maybe between C and B, there was a very big difference and a lot of judgment required from the geotechnical engineer. Does this kick us into B, or is this up in the C value? And now we can use a very specific VS30, which is normally advantageous. You can see for the majority of this graph, using VS30 is actually beneficial. One of the reasons we should use VS30 in our preliminary design rather than just relying on the site class. That said, we can still use these site class values for preliminary evaluations. And the way it's measured, is a big change. This is a change not in the building code itself, but in the commentary to the building code, where previous industry standard was to measure VS30 or site class from the foundation elevation. So you can see on the left-hand image, what we used to do is we would excavate for the building foundations and we would measure VS30 from the base of the foundations, because that is where, that's where the majority of the loads are imparted on the building through the foundations. Seismic load is really inertia load. The building wants to stay still, the ground is moving. As the ground moves, the inertia of the building imparts seismic loads on the building components. However, the new commentary to the code indicated that we need to now measure from the surface, not from underside of foundations. And this has a great impact in Victoria, especially. It does in some areas of Vancouver as well. It has a very big impact in Victoria because many of our sites have very soft soils overlying very hard bedrock. So we have what's called high impedance sites, where there's a very big difference between the soil in the upper few meters and the bedrock below that. There's been some of these graphs and some of this content comes from a few months ago, and we didn't have further clarification to the commentary. We've had a fair bit of discussion as an industry around the commentary. We're working with UBC on some research. There is information coming here. Right now, it looks like we'll be calculating VS30 from halfway between the surface and the foundations. That has a lot of precedent in the States. but we're advocating for specific sites with high impedance that we continue to measure from the underside of foundations. And it looks like we may be able to do that moving forward with some additional testing required on some larger projects. So that's a big change. Some of the slides where I talk about some of the future slides here when I talk about the impact of the code change, we will be assuming that we're using the right-hand diagram and the measurement from surface. That's already been mitigated a little bit. So just to give people an idea of the magnitude of the change on Vancouver Island, this graph indicates the change for various building typologies over the code baseline in the last two code changes. And so you can see for concrete high-rise in Victoria, for a typical Victoria concrete high-rise, we've seen a 610% increase in seismic forces since 2010. That's a combination of the higher loads due to that new fault line and the change in site class due to measuring VS30 from surface rather than from subgrade. I'll talk a little bit more about site class impact on building design, but very, very significant. And we have projects in for rezoning development permit with assumptions around floor area and sizes of the cores, et cetera. And this has had a really, really big impact on the viability of some projects on Vancouver Island. For the smaller sort of mid-rise and wood frame projects, the impact is less, but it's still quite a significant impact, as you can see from the blue and the orange lines there. Potential ways to reduce this impact. Measure VS30 for the project site. We've talked about that at length. Just do it. It needs to happen anyway. Might as well do it early in the project and get the best information. The geotechnical engineers have a number of ways to measure VS30. So we can talk to them about that. I think, Nick, you've had some geotechnical input on these seminars as well. Embedment factors. This is what I talked about, using VS30 from halfway down rather than from surface. So there's some ongoing work and research on the embedment factor calculations. And then site-specific seismic response analysis as well. Okay, talking a little bit about seismic risk. When we design, the way the code is written is we're designing for a very rare but very intense earthquake. So that 100% code earthquake that you see on the left of the graph, which is the 2% in 50-year probability. So there's a 2% in 50 years that we'll see a code level earthquake impact our buildings. So the majority of the buildings we're designing are unlikely to ever see a code earthquake. However, they're quite likely to see a lower magnitude earthquake that's still considerably damaging. And this is one of the pieces that the code is covering, is that we're going to see we need to design for the 10% in 50-year earthquake. So we're designing to stop the building from collapsing in the very, very big earthquake, and we're designing to stop the building having significant damage under the more minor but more frequent earthquake. And there's not a linear relationship between these things. So when you sometimes hear structural engineers talk about 70% of code or 50% of code, they're not very accurate ways of describing the reduction in risk. It's much better to talk about the probability of exceedance. And so when we talk about doing seismic upgrades for 70% of code, really we should be talking about doing the 5% and 50-year probability of exceedance, not 70% of code. Those numbers do get interchanged a fair bit though. Okay, impact of site class on our building design. What does that actually mean? Like, we saw that step function. What does that impact on site class actually mean for design? So this is an example for Victoria, 6-story wood frame with gypcrete topping. These graphs change a fair bit if we don't have the gypcrete topping. These are the graphs for 6-story wood frame with topping. Site class A, we're designing for about 13% of the building weight in Victoria. In Vancouver, that would be about 7 or 8% of building weight, but in Victoria, it's about 13%. If we go from site class A to B, that increases to 17% or 30% increase in load. If we go to C, it's 30% of weight or 2.3 times the forces for A, and D or E is 3 times the force. So in Victoria, same type of building, same design code, same building weight, same floor-to-floor height. We could be 2 blocks apart, and one building could have 3 times as much shear wall as the other building. There's a huge, huge impact in terms of site class and what it means for building design. And that's what I'm hoping to convey on this graph. The other thing I'm hoping to convey on this graph is as you see that curve, what that indicates is on the right-hand side of the graph where the curve flattens out, those shear walls are strength governed. As we move left and the shear walls get shorter, they become increasingly deflection governed, and they become less effective because we have to stiffen them up for deflection, and that then attracts more load. And so we see the curve means walls for site class C and D and E become very ineffective as the walls get shorter than about 4 meters. I'll explain why in some coming slides. But remember that as structural engineers, we're always balancing strength and stiffness or sway. The building code allows us to let the building sway a certain amount, and we want the building to move and dissipate energy. That's where the ductility comes from. The ductility comes from building components and overall building moving and dissipating energy. But we don't want the building to move so much that we damage the operational and functional components or the windows or cladding. We want to limit that damage through reducing deflection or sway, but we want to allow as much deflection or sway as possible to increase the ductility. And that's where that curve comes from and that balancing. Okay, deflection of it. We'll get a little bit more technical here. If I lose you, just put something in the comments and we'll use less equations, etc. But I wanted to explain deflections in wood-based shear walls. This is an example for a single story, but it's extrapolated over multiple stories. The contributors to deflection in a wood frame shear wall are deflection due to overall bending. That's the first term here, which is, as you would imagine a cantilevered beam supported at the foundation, it wants to bend. The other piece that allows the wall and the building to move is deflection due to panel shear. So as we change our panel shear thickness from, say, 1/2-inch plywood to 5/8 to 3/4 inch, the shear deformation becomes less. There's deflection due to nail slip. This is quite significant deflection due to nail slip. And so then the nails want to move between the stud and the plywood. That's where all the ductility comes from. So that's the secret sauce to wood frame shear walls and why we get to use such a large ductility modifier is all of those millions of nails that we see in a wood frame building bend a little bit and deflect and generate heat as the building moves and the shear wall deforms. There's deflection due to vertical elongation. This is those tension cords at the end, Simpson ATS rods or similar, that are deflecting as the building moves. And this is the largest variable. So this is the one you see, you'll see us speccing very, very large tension hold downs now in projects. We're doing that not necessarily for strength, but to fight deflection. You'll see 2-inch diameter steel rods there now on some of our projects on Vancouver Island. And then there's deflection due to rotation at the bottom of the wall. This one's relatively small, but it starts to add up as we stack these walls on top of each other. So that's just a little bit of background. A shear wall is kind of like an I-beam or a TGI joist on its edge. We want to stack the mass and the structure as far to the ends as possible. That gives us a lever arm to resist deflection and increase strength. It's also why we want to see these walls be as long as possible. Little 2-meter walls are much, much less effective than long sort of 4 and 5 and 6 meter walls that we can achieve as party walls or in the corridor. We'll talk about layouts and optimizing of the shear wall layouts a little bit further along here. Some other miscellaneous things that affect the lateral load on these sorts of mid-rise wood frame projects. And apologies for the funny diagram here. It's just we've been using this one for months and it was easier to copy it over. A typical mid-rise wood frame that sits on 1 or 2 levels of parking at grade, we can just design that as a 6-story building. It's a 6-story wood frame building. It's lightweight. Its base is the foundation that lands at grade, and that's where the seismic accelerations come from. It's relatively straightforward, has a reasonable amount of shear wall, etc. However, a lot of zoning requirements, developer requirements require that we have some underbuilding parking or we have some commercial space on the main floor, which then raises up our wood frame above grade, requires some sort of transfer level at level 2, whether that's steel or concrete, and dramatically increases the weight of the building. The weight of that transfer level at level 2 could equal the entire weight of the 6-story building above or the 5-story building above in this case. We then have to accelerate all of that mass in our seismic models and resist that overturning. So rather than having a lightweight building that ends at grade, we have a lightweight building ending at level 2, turning into a heavy building that wants to accelerate above level 1. And because it's a relatively squat concrete structure, we don't get to use those nice ductility modifiers that we use for a tower. And so we have a rigid and strong concrete podium, which results in very, very large foundation forces. So as soon as we push that building above grade, there's a very large impact on project cost, project material usage, carbon impact, etc. So we're an advocate for, if it's possible, to work with the zoning and the planners and minimize as much as possible those transfer levels or heavy L2s in mid-rise wood frame. The image on the third is just when it's even further exacerbated by, wanting some overheight space, some CRUs, etc., on the main floor that push that building up even higher and increase the lever arm down through the foundation. Another thing that probably everybody knows by now is the new letters of assurance require that all structural designs have independent reviews prior to building permit. This is something, it doesn't really have an impact on the overall work or what's required. What it does have an impact on is schedule, in which we used to be able to submit building permit drawings sort of at 80% complete, and there was quite a bit of tidying up to do, but there would often be some last minute work to get ready for permit, and we would be able to submit those on a relatively tight schedule. That's no longer as possible when we need to complete that independent review and address the comments prior to building permits. So we just need to leave a few weeks in our schedule on current projects so we can get those independent reviews done prior to building permit rather than prior to construction. Okay, some of the practical aspects, impacts on layout systems and cost, as we talk about seismicity and its impact on building design. A couple examples from Victoria. So here's an example of a typical sort of Victoria concrete tower, and the zoning requirements that say, hey, we have to create a podium effect. We have to step this in. We have to step it in up above. We have to create activation at the street for CRUs, etc. Which in this case, what it did, and you can see it really nicely on the section. And I love to think about building structures in section. Building sections are just so informative in terms of how the building actually goes together, and you can look through. We can easily see on the building section that we have those transfers and offsets that create and where it creates weight to the structure. You can see that level 2 structure got very, very heavy on this project because the residential unit alignment doesn't align with below. And that mass above grade needs to be accelerated seismically and contributes to the overall seismic load. In this case, was about a 15% increase in seismic load, which means the core walls got 15% thicker and the core foundation got 15% larger. It has a material impact on structural cost. This is avoiding transfers is one of the best things we can do to minimize structural mass on a project. An example here, sort of the counter example, is a 6-story wood frame that just lines up down to grade on a relatively simple parkade. Everything lines up here. Everything's doing a simple job. It's, this is the way to reduce cost and improve simplicity, which definitely doesn't mean every building has to be a box. What it means is that we need to simplify where possible, because simplification equals efficiency. That's generally the way it is. If we add complexity, we need to be really, really careful and work together as a team to minimize the impact of that added complexity. And there's lots of ways to do that, lots of efficient ways to do that. But that's back of mind. That's where we want to be heading to. Another example, this is kind of middle ground. This is what a typical mid-rise wood frame looks like. We'll have multiple buildings on a podium. We'll have some transfers and some complexity, and we'll work through that to do that as light as possible with wood framing. I love the image on the left. To me, it explains why light wood framing is so very efficient. It is, the mass of structure required to support the building is so very, very light. It's very, very efficient. We're using interior partition and party walls to demise the space, but also to provide support for the structure. And we don't actually need much more support for the structure than we need support for the drywall cladding and exterior wall cladding. It's a very, very efficient and modular way of constructing buildings. Okay, some strategies and resources for collaboration here. Back as a reminder, back to the formula and where this is coming from, because we want to focus a little bit on the mass factor. Sorry, the mass factor. and the ductility related force modification factor. Reducing mass is the simple and easy way to reduce the seismic load on buildings. As we saw in the formula, the seismic load is directly related to mass. So anything we do to reduce the weight of a building reduces the seismic forces. The first thing we consider when we have, when we get into poor site class C or worse on Vancouver Island, probably site class D or worse on the mainland, is the removal of concrete topping so that we can reduce the weight of the wood frame building by about half. So that 1.5 inch of gypcrete or concrete topping is almost as heavy as the rest of the structure and finishes combined. So getting rid of that topping goes a long way to reducing our seismic force demand. We can do similar things in concrete buildings. The better way to do it in concrete buildings is to reduce the spans, is to go, get down to something like 18-foot spans so we can have reasonable slab thicknesses. The thinner the slab, the lighter the building. And reducing transfers, as I showed in that example at 1400 quadra there. The other thing that I think it's worth mentioning, and we have some slides here coming up as well, is that anything we do to reduce the structure mass also reduces embodied carbon, right? As we use less material, we're more sustainable, we're more cost effective. All of those things, sustainability, cost effectiveness, seismic force reduction, they're all working on the same team. These aren't competing priorities. Almost anything we do to help one of those things is also helping the other. Focusing a little bit on those RD or not values, the ductility force modifiers, and I've just shown the SFRS here for timber structures, just to give you a comparison, but we can give some examples here for concrete, steel, mass timber as well. Those nail-based shear walls with wood panels, we get to use an RD factor of 3, which means we get to divide our seismic forces by 3 and use a much, much lower seismic force for nailed shear walls. As we go down into using gypsum panels or cross-laminated timber shear walls, etc., you can see that denominator gets smaller, in which case our forces are going up quite significantly. So what the code wants us to do, what the dynamic models want us to do is allow a fair bit of movement in a controlled way, which is what the ductility is, and why we love those nail-based shear wall panels. We get millions of nails all bending together, all dissipating energy in a very predictable way, predictable and safe way. Irregularities, I mentioned this early in the presentation, is the code has a list of irregularities that cause us to either increase the seismic forces or increase the analysis procedures. We have to go away from the equivalent static to the dynamic procedures, but there's some things in here. Anything you see in this list is a bit of a red flag that it's going to cause some complexity and some cost and some increased forces to our building designs, which is anytime we try to have geometric irregularities, or we try to offset our shear walls, or we try to move them out of plane, or we have weak stories. We definitely don't want weak stories in any of our buildings in high seismic zones, or torsional sensitivities. And then I mentioned those gravity-induced lateral demands and the sloped column irregularity. So those are things to watch out for. Your structural engineer on your project will mention these if they see them as well. We sometimes see these early on. We get an RFP or a proposal that has some big cool V columns or something. We'll often flag that even in our proposal that say, we need to be really careful about V columns or sloped columns under the new code, where it was relatively easy before. I thought I would spend a little bit of time just chatting through optimal heights by structure in the various areas of the province and soil conditions, because this is a question we get, early on in projects. Developers, architects will call and say, hey, what can we build on a site? I have a geotech report. It says site class D. It says 2 stories of clay. What can we actually do? What does that mean for the project? And so a lot of what sets the optimal building structure is the code and what's allowed in the code. So 6 stories or less, we can go combustible construction. We can go light wood framing, right? Light wood framing is cost effective, lightweight, simple to build. 6 stories and less, if the occupancies allow it, we almost always want to go light wood framing. Whether or not we have an underground is up for grabs. It's nice if we don't need an underground. In lots of areas of Victoria, we have compressible clay at depth, which means if we add any weight to the building site, we run the risk of compressing that clay slowly over time, in which case we have to compensate, which means we have to excavate down anyway, we often have to excavate down a story or so to compensate for the weight of a 6-story building. You might as well build a parkade in that case. So it's almost a free parkade on those sites with compressible clay. Once we get over 6 floors, and this is sort of a residential discussion only, not other types of buildings. Over 6 floors, we run out of combustible construction with one exception, and the number of building systems increases dramatically. So, from 7 to 18 stories, we could go load-bearing steel stud, we could go reinforced concrete, we can go steel. There's a number of different options. I think in general, and this is for Vancouver Island, in general on Vancouver Island, concrete buildings are not economic until we get to about 17 or 18 floors. Those sort of 12, 14-story concrete buildings, very, very hard to make economical in a high seismic zone. Better to keep the building lighter and do something in mass timber, maybe with a concrete core, load-bearing steel, maybe some lightweight floor assemblies, and use sort of those middle ground structures in those areas. In Vancouver, it's a little different. In Vancouver, we can kind of make the 10 to 15-story concrete tower work with half the seismic loads depending on the soil conditions. So there, it's maybe a bit more of a toss-up between mass timber and reinforced concrete. Once we get over 18 stories, we can't go mass timber anymore, even encapsulated, unless we go far outside the code, which is fun, but probably not right for most projects. So once we're over 18 stories, it's generally reinforced concrete with a centrally located seismic core in southwestern BC. That's very, very efficient building typology. I actually attended an internal seminar at RJC yesterday from our Toronto office, talking about super tall and high-rise buildings and doing efficiency comparisons. And they thought when they ran their meta-analysis that they were going to find that Toronto buildings were more efficient overall than Vancouver buildings because of our seismicity and the requirement for big, thick cores, etc. But actually, it was the opposite. Their buildings in Toronto tend to be heavier and more carbon intense than our buildings on the West Coast because of all those rules, those irregularity rules that I explained in the code in the high seismic zones. Keep our buildings relatively simple and straightforward as compared to the Toronto buildings where they have huge podiums, offsets, all of that sort of thing that really increase the structure weight and the carbon intensity for their buildings. I thought that was interesting. This is from Half Climate Design. I thought I would include this as well. There's a lot of really great resources that layer on carbon intensity on top of structural requirements, on top of use and occupancy requirements. And I think I'm a structural engineer, so I'm obviously talking from a structural engineering lens when I think about reducing seismic load and all of those things. But like I said, we're all on the same team here in terms of wanting to use our materials efficiently. And the building layout and the number of transfers in the building form have a huge impact on carbon intensity and building weight. So it's really worth thinking about that as a team, architect and engineer, to try to keep that as efficient as possible. Okay, floor plan impacts. Here's a typical but also exceptionally well planned and thoughtfully laid out floor plan by one Nick Bray. And I just wanted to chat through how, as structural engineers, how we go about determining where and how we'll use shear walls. And so if you think back to that graph where I showed those curves of the effectiveness of walls, we know that walls under about 4 meters don't contribute much to lateral force resistance. So we know we can see these sort of 10-foot-ish walls around the perimeter, or these 4-foot sections. None of those are worth using. If we were to use a little wall like this little wall is about 1/4 as effective as this long wall, which means we need 4 of them, but each of them would have exactly the same size hold downs and stud packs, etc., as this big long wall. So we're much, much better off finding and using only the long walls and then increasing, if necessary, the diaphragm to drag the loads over to those longer walls. So with this type of floor plan, with lots of smaller studio type units and lots of doors in the corridor, we find often that we have lots and lots of wall in the party wall direction. So in the north-south on this page, we have no trouble finding enough shear wall in this floor plan in the north-south direction. However, in the corridor direction, it becomes very challenging. So when we have these smaller units and we have small runs of corridor wall, we have trouble finding enough corridor wall to resist the seismic forces. There's a few things we can do around that. In this floor plan, it's nice that we have some end units with a longer party wall, so we can pick up and use these nice long walls at the end. We also have this nice wall behind the elevator shaft. One thing we can do here, and we sometimes chat about this in prelims with designers, is if it's possible in these units to even bunch these corridor wall openings even a little closer together to bunch the entries. If we bunch the unit entries, we get longer runs of corridor wall, which is more effective for us. The other thing we can do, and we've been doing that on some projects now with the higher code loads, is doubling up walls. And we might say, hey, we're about 50% short in the corridor direction. We're going to make some of these walls double walls, so 4 layers of sheathing and 2 separate stud walls, perhaps here and here and here, the long walls that are the most effective, and make it work that way, rather than trying to go interior and picking up little bedroom walls, etc. It's very difficult to do that. We end up chasing our tail on that. On the sort of flip side is projects with larger unit sizes. So a project like this with larger unit sizes, you can see now we have corridor walls, long runs of corridor wall. It's no trouble at all making the corridor work, but because the units are larger, now the party walls are challenging. And so we may have to double up some of these party walls or make some other changes to make them work. One thing I'd like to point out is these little exterior extensions where the party wall goes from interior to perhaps shared exterior-interior wall. It gets to be challenging from an energy modeling and building enclosure standpoint when our hold down and stud pack, and that hold down, like I said, that could be a 2-inch diameter rod, and the stud pack could be 16 2x4s. It's a lot of material, and it impacts the amount of insulation and increases the thermal bridging in those areas. We prefer not to use those little extensions into the exterior. That said, I'd rather extend this wall there and maybe do some exterior insulation than to try to grab some interior walls. So we're always playing around with balancing how much wall we need, which wall is the most effective, what comes with the least cost. And if we can get together early in a project and lay out the units in such a way, maybe we need to move a mechanical shaft or adjust a unit entry in order to make it work in a more conventional way. That's much, much easier to do in schematic design than as we get into working drawings. Okay, so we talked about reducing the load on the buildings. What about resisting the load on buildings? This is the VR side of the equation. I like to show this image. This is a test from a Simpson strong tie hold down in a 12-inch concrete slab, and you can understand the magnitude of the force when you popped out all of this reinforcing in concrete under the load from that hold down. They're very, very significant hold down loads, sometimes 200,000 pounds. We'll talk about how to do this in concrete buildings, wood buildings, etc. And I recognize that we're running towards the end of your lunch hour, but I think we're on slide 37 of 43, so we're doing really good. On a concrete tower, the unfortunate answer is we don't have a lot of flexibility. We're already using a very ductile system, often with an RD of 3.5 or even 4 for coupled shear walls. So we have a very, very ductile, controllable lateral system. It's the default on the West Coast for concrete towers. The unfortunate thing is we're already maximizing the resistance of these towers in our current designs. They have as much reinforcing as the code will let us put in them, and we're using 60-65 MPa concrete for these cores. So the answer under the new code loads is your core walls are going to get thicker. So allowing for those thicker core walls. An example here from Vancouver Island where a core was 2'4" before and is going to 48 inches wide. In Vancouver, that might be something that was 18 inches going to 2'6". That's the sort of magnitude of the change we're expecting or we're seeing in concrete towers. And this has an impact on your project for, there's not just the added structural cost for that concrete and reinforcing. You're losing saleable floor area. You're increasing the carbon intensity. You're doing lots of negative things to the building. In wood frame, there's a few things we can do. One of the things that's sort of easy and relatively exciting for us is the introduction of mid-ply shear walls in the code. We're now allowed to use plywood and OSB sandwiched in between 2 studs, where we get to use that nail in double shear. So if we imagine what was previously a wall sheathed both sides, we can add 2x on the flat on one side of this and run these nails through that flat 2x into the wall stud. And this nail gets to be used in that ductile shear bending 2 times. So we get to use this nail twice and this nail once. Just doing this gives us a 50% increase in the shear resistance of this wall. So a really nice way to increase the shear resistance of these walls using the mid-ply technology. So that's a really nice development that we're already implementing on some of our designs on Vancouver Island. Part 11 of the Vancouver building bylaw upgrades, new loads. I don't know if I can do that today. I might have to get back to you, David. A few other systems that are applicable to some projects and not others, and I think it's just worth maybe running through a few of these and mentioning some pros and cons. Simpson strong walls, we see these get used very frequently on single-family homes, townhouses, low-rise projects. Really, really effective, really nice for the sides of garage doors, etc., where rather than maybe using a moment frame, we can drop in some Simpson strong walls with some anchors to the concrete. Works really, really nicely. Proprietary, easy to source, all of that stuff. CLT shear walls, when we show those ductility calculations and you see that the RD are not drops from 3 and 1.6 to 2 and 1.4 because CLT shear wall doesn't have any inherent ductility. It's a big, super strong mass of wood and doesn't have any inherent ductility. The way we introduce ductility into CLT shear walls is proprietary hold down systems that provide us that ductility, such as these Tectonis anchors. So that's a way we can improve the ductility for CLT shear wall systems. I don't recommend trying to put CLT shear walls in a conventional wood frame building, like a mid-rise building. They're heavy and less ductile and more expensive. We should save those for the times we need them for fire resistance ratings or other reasons or inside of mass timber buildings. We're doing a mass timber fire hall in Victoria right now, and we've got some CLT shear walls in that guy using Tectonis. It's a good system for that. CLT floor panels on mid-rise wood frame. It's a great option. There's definitely some pros and cons to going CLT floors instead of TGI floors. It's a little bit faster. It's a little bit thinner. It's a little bit simpler. You don't have all of the clips and screws and anchors and sill plate A nailing and sill plate B nailing. There's lots of reasons it's great. Some of the drawbacks are you can't really go as far with the spans. We can really only go about 13.5 feet with 3-ply CLT. If we go longer than that and we kick into 5-ply CLT, the cost just gets to be too high. And so there's sort of a sweet spot with small units and CLT floor panels for conventional wood framing. Steel moment frames are an option for sort of lower rise stick frame buildings where you really need a lot of open space. I'm not a big fan of mixing moment frames into light wood framing. I would rather upgrade the diaphragms and drag the load to a shear wall back further from the facade if possible. If it's not possible, we can certainly put steel moment frames into wood frame buildings, as we've shown here. Base isolation, I think this is coming. I think, as the loads change, as the technology advances, this is commonplace in Japan. In Japan, renters are willing to pay a 30% premium to live in a building that's base isolated versus not base isolated. I think it's coming here. I think especially if we experience some moderate earthquakes and we see the damage, I think there'll be a move towards base isolation. We've done a couple of feasibility studies on Vancouver Island to study the feasibility of base isolating a mid-rise wood frame off its podium. Right now, it's not economically feasible, but it's close. It's getting to be close where we might be base isolating at level 2. For instance, we build the podium, we base isolate at level 2, and we introduce a 5-story wood frame that's base isolated from the rest of the building. So we'll see that coming. Interesting stuff. Buckling restrained brace frames. Very, very efficient. These are highly ductile. We get to use RD values of 4 when we use buckling inhibited braces. Mixing these rather than using a steel moment frame, perhaps in some places where we have some CRUs or open spaces in buildings, these work really, really well and are worth considering on some of your projects. Questions. I do see some questions sort of coming through here, and these are great questions. I would love to quickly sort of chat about a couple of these. Mid-ply shear, certainly problematic for acoustic values. We would probably see those in corridors. The way to avoid the acoustic is to add some hat track or some layer, deal with acoustics separately from from the mid-ply shear wall, but certainly impact. NLT instead of CLT, the downs, there's NLT has the upside to NLT is all your fibers going in the same direction, so you can achieve longer spans with the same amount of timber as you can with CLT. The downside is you have no diaphragm capacity. Because all the fiber goes in one direction, you have very, very limited diaphragm capacity. And so it's only good for one-way spans, and it's not great for your diaphragm. So that's why you often see a layer of plywood added to NLT floors. Moving to staggered studs, of course. So standard assembly for mid-rise wood frame is we stagger studs in the corridors to allow that better acoustic separation between the unit and the corridor, and then at the party walls, two separate independent stud walls with an air gap is generally our approach. We sometimes see staggered studs there as well. It's just not quite as good as two independent 2x4 walls with an air gap. There are no mid-ply shear wall assemblies tested for fire ratings. No. So it would be the additive method, and you're protecting these walls with gypsum panels anyway. We're not getting any of our fire rating in a mid-rise wood frame from the value of the studs, etc. That's all coming from your gypsum panels. So no, I don't believe that we need additional fire testing for mid-ply shear wall assemblies. They don't. Bruce's question about elevator cords, no, it doesn't change. And that's something I should have mentioned. I think when early days when we allowed mid-rise wood frame in BC, we saw those laminated 2x6 elevator cores. We don't do that anymore. We protect our elevator cores with gypsum. We don't rely on timber to protect the elevator core assembly. And so right now what we do is we build a conventional 2x6 elevator shaft with a separate 2x4 wall for acoustics. And then we put in some large PSLs for the elevator manufacturer to connect their equipment. We don't try to use that laminated assembly anymore. We ran into a number of issues with that. You certainly can't use block walls or concrete walls in mid-rise wood frame. So that's just an absolute no-no. Please don't try to spec concrete block or concrete elevator shafts in anything more than 4 stories of wood.
On that same subject of acoustics, actually, you had a great slide in there, Leon, relating to the Suprema system for
Yep.
eliminating the topping for concrete topping for
Yes.
buildings. And we did wasn't that long ago, we completed it a mid-rise buildings with you and your team. I can say, because we were apprehensive of using that system,
Yeah.
eliminating topping and just having it's basically it's a Suprema system with a mat above the plywood, and then it's their own system for a clip system and kind of res bar type system below that assembly. And I can we test it after they put that in, and it works. Like the builders had their stereo system cranked up on one floor. We went into floor below and we couldn't hear it. So
Yeah.
I'm pleased to be able to pass that on, that those systems do work, and it enables us to not just bring down the weight, but as you said, the embodied carbon in these assemblies. So yeah,
Yep.
that's a great.
Absolutely. They do work well. They're a bit more complex to install. There's a bit of sequencing and installation finickiness, but the majority of our builders are familiar with those systems now, and it really works quite well. And the thing when we're comparing cost, and it may be that assembly costs a little bit more than the concrete topping, but the thing to remember is that the weight of that concrete topping impacts the transfer level, the foundations, the seismic system, all of that gets added on, which is often difficult to account for. But what we found, some of our clients have switched completely to using acoustic systems only. Even when we have good site class, they're still using those acoustic systems and eliminating the topping. Structural diaphragm upgrades to deal with high capacity shear walls mid-ply. For sure, we would still, regardless what system we're talking about here for mid-rise wood frame, we still want to stick with a system where we have a large number of shear walls with relatively small diaphragm spans. So our diaphragms are never spanning more than approximately a unit, sort of 30, 40 feet. That's the maximum diaphragm's ever going to span. We can achieve those diaphragm spans with our typical 5/8 or 3/4 inch plywood with blocking and nailing relatively easily. We haven't run into any issues in mid-rise wood frame with diaphragms failing.
Yeah, just to wrap this up, we're getting close to the hour here. But I think that one of the biggest takeaways for me, or the most enlightening thing for me when we first discussed this, was how those the decision, that early decision you make to when you choose that structural system, how that's changed in the new code. And you mentioned, yeah, especially with concrete high rises in Victoria, like 17, 18 stories is yeah, that's where you want to be to make that make any sense.
Yep.
Obviously slightly different in Vancouver, but yeah, I mean, maybe you could just run us back through those because just that quick comparison. My understanding, obviously, we all know that 6-story wood frame is sort of 6 stories and below. But yeah, maybe compare that to the lightweight steel stud, the
Sure.
yeah, CLT, and maybe even heavyweight steel as well.
Yeah. So light wood frame, 6 stories and less. Load-bearing steel stud, effective to about 10 floors. So after about 10 floors, there's so much red iron required and heavy gauges that it starts to be uneconomic. But from 7 to 10, load-bearing steel stud is quite effective. And that height is limited by gravity requirements, not seismic. And in those systems, we would see either concrete cores or steel frames, with some combination of those two things. Mass timber, we can go to 18 floors. There's some incremental steps there in terms of encapsulation and protection during construction as we get over thresholds of 12 stories. But really, really good option for up to 18 floors in our current codes with mass timber, which is about 30% lighter than an equivalent concrete building. So really, really good option for buildings in that sort of 8 to 18 story range is mass timber. Structural steel buildings, we don't see it much on Vancouver Island. We don't have as many qualified steel trades on Vancouver Island. I think it's relatively similar in the Lower Mainland as well. We just don't see a lot of steel construction because we have the benefit of a milder climate. We can pour concrete year round. We generally kick over to concrete once we're into high-rise buildings. Also durability, et cetera, and all of those factors. The threshold for that concrete building, that sort of 17, 18-story threshold I mentioned, was for Vancouver Island, where the core walls just get to be so thick for the actual volume of the building when our building is short and not flexible enough to dissipate the energy that we want it on Vancouver Island. We'd rather go taller with a smaller floor plate in terms of overall structural intensity on Vancouver, in Vancouver, or the rest of the country where the loads are smaller. That threshold kicks down, and we can build a 10-story concrete building that's relatively efficient. It's just that threshold bumps up a lot when the seismic forces bump up so high here. How much are they swaying? That's a good question. As I said, we try to let them go the maximum. So the code lets us go 2.5% of story height with our deflections. It's impossible to tune a building so that every story goes 2.5%. So overall building average generally with mid-rise wood frame is 2% of the building height. And that's the distance we need to keep it off the property line. So don't forget about that. We've had projects where, they're designed to be tight to the property line, and people are forgetting that we need about 14 inches of distance from the property line in a mid-rise wood frame. The NIMO is quite a bit lighter, Marta. Loads in a NIMO are about 30% lighter than they are in Victoria. Depends on site class, obviously, but it's quite a bit lighter in a NIMO.
Fantastic. Well, thank you very much, Leon. I really, really appreciate you giving this lecture today. No, it's been incredibly informative. We will be emailing everyone that attended with a video so they can look back at anything they want to revisit. As I said, we'll also be keeping you informed about those potential lectures coming up or seminars coming up in September as well. But thank you everyone for joining us today. Thank you again to Leon, and yeah, we hope to see you soon.
Thanks so much, Nick. Thanks, everybody.